All right, so for problem 3, we're given this sequence here where A1 is 1/2, A2 is 1/4, A3 is 1/8, and so on. If we're looking for the formula for A of n, the thing to note is that in every term the denominator is multiplied by 2, and so what we get is that A of n is 1 over 2 to the n. And once again, you can verify that that actually does work for the first few terms. All right, so for part B, it asks us to find the limit as n goes to infinity of A of n. Well, this one just ends up being limit as n goes to infinity of 1 over 2 to the n. And so we get something that's 1 over infinity, or it approaches 0. Now in part C, once again, we want to look for a pattern in the sequence of partial sums. And so if we look at S1, it's just the first term, which is 1/2. S2, it's 1/2 plus 1/4, which this ends up being 3 over 4. S3 is 1/2 plus 1/4 plus 1/8. If we add those up, we should get 7 over 8. If we continue this for S4, when we add up A1 plus A2 plus A3 plus A4, we get that this is equal to 15 over 16. And so if you see this pattern here for S of n, we should get that, so our denominator here is just our 2 to the n. It's the same as the denominator of the nth term of the sequence. If you look at the numerator, this is just 1 less than the denominator in all of these terms. So it is equal to 2 to the n minus 1 over 2 to the n. And another way we can write this, which will allow us to see the answer to part D a little easier, is that we could write this as 1 minus 1 over 2 to the n. So now if we look at our answer for part D, we can take the limit as n goes to infinity of our S of n, and so this is limit as n goes to infinity of 1 minus 1 over 2 to the n. And once again, this is equal to 1. If you note that this 2 to the n term approaches 0 here. For this particular example, I have a visual of what's going on that might help you see how adding up all of the terms in this sequence gives us a series which adds up to 1. So we have our series 1 over 2 to the n, which is the sum of these terms. And so if we look at this square here, now suppose this is a square where the total area of the square is 1. The first term can be represented by the 1/2. And so that's area 1/2. Now the next term is area 1/4. So we can put that one in there too. The next term is 1/8. And the next term is 1 over 16. And so you can see that then 1 over 32 is going to be half of what's left in that square there. 1 over 64 is going to be half of what's left. And the idea is that that space in the upper right-hand corner of the square that's not filled in, it gets smaller and smaller and eventually approaches 0. Thus, we get that the sum of these infinitely many terms adds up to 1.